Hello everyone. Very good evening to all of you. Good evening everyone. Good evening. Am I audible, visible? Please type in a chat box. Am I audible and visible? Okay, so shall we start today's session? Shall we start today's session? And please let me know whatever we discussed in the previous class that is clear to everyone. In previous class, we discussed about the kinematic viscosity, right? In previous class, we discussed about the kinematic viscosity. uh, we started application of the Newton's law of viscosity, and we discussed, I think, one or two cases, I think. Okay, so in previous class we discussed about kinematic viscosity, right? And what is a kinematic viscosity? That kinematic viscosity is denoted by Greek letter nu, right? Kinematic viscosity is also called momentum diffusivity, and why it is called momentum diffusivity, that already I discussed, right? The momentum diffusion from one layer to another layer of a fluid, that depends on the kinematic viscosity, that depends on the ratio of dynamic viscosity to density, and that property, right? Because dynamic viscosity is a property, density is a property, so definitely that ratio is also a property, right? So the momentum transfer from one layer to another layer, that depends on the ratio of dynamic viscosity to density, and that ratio is another property, and that property is known as the kinematic viscosity or momentum diffusivity, right? So kinematic viscosity is dynamic viscosity, it is ratio of dynamic viscosity to density, right? Dynamic viscosity to density, right? And what is the unit? What is the unit of kinematic viscosity? So we already discussed about SI unit. So that SI unit, that is meter square per second, right? If I'm talking about the MKS unit, that MKS unit, that is also meter square per second. And if I'm talking about the CGS unit, if I'm talking about the CGS unit, so that CGS unit is centimeter square per second. And this centimeter square per second is called, this centimeter square per second is called Stoke, right? This centimeter square per second is called Stoke, and 1 Stoke is equal to 1 Stoke is equal to, you can say this is 10 to the power minus 4 meter square per second. Are you able to write in terms of fundamental dimensions? Are you able to write in terms of fundamental dimension? Can you write kinematic viscosity in terms of fundamental dimensions? So yes, we can write. So kinematic viscosity in terms of fundamental dimension, this is L square T minus 1, right? L square T minus 1. So this is the kinematic viscosity in terms of fundamental dimension, L square T minus 1. Now can you tell me what is the effect of temperature on kinematic viscosity? Can you tell me effect of temperature? Effect of temperature, effect of temperature on kinematic viscosity of fluid. Effect of temperature on kinematic viscosity of fluid. So what happened in case of gas and what happened in case of the liquid? So if I'm talking about the liquid, if I'm talking about the liquid, so what happened in case of the liquid? what happen in case of the liquid, what happen in case of the liquid as the temperature increases, as temperature increases, what happened with the kinematic viscosity of liquid? It increases or decreases? It increases or decreases. So we already discussed, as temperature increases, kinematic viscosity of liquid decreases. As the temperature increases, kinematic viscosity of liquid decreases. Now if I am talking about the gases, if I am talking about the gases, what happen in case of the gas? As the temperature increases, as the temperature increases, kinematic viscosity of gases increases, right? As temperature increases, kinematic viscosity of gases increases. So that part we already discussed, right? And also, if someone asks you which having more kinematic viscosity, liquid having more kinematic viscosity or gases having more kinematic viscosity, so answer is simple, we can't say, right? Kinematic viscosity of gases, there are possibility the kinematic viscosity of gas is more than the kinematic viscosity of liquid, or kinematic viscosity of the liquid is more as compared to kinematic viscosity of gases, right? So if you compare the gases and liquid, you can answer in this way. But if you compare kinematic viscosity of air and the kinematic viscosity of the kinematic viscosity of the water, right? If you compare kinematic viscosity of the air and the kinematic viscosity of the water, then you can easily say kinematic viscosity of the air is greater as compared to the kinematic viscosity of the water. That we already discussed with the help of graph. We already discussed with the help of the graph, this graph, right? That part we already discussed. So better, that is clear to everyone now. That is clear to everyone now. So please type in a chat box, that is clear to everyone. That is clear to everyone. Okay. Now come to the next part, which is a application of application of Newton's law of viscosity. Application of Newton's law of viscosity. So this is the first application, and in this application, bottom plate is fixed and top plate is moving with constant velocity. So if I ask you what is the power which is required to maintain the top plate velocity as v, what is the power? So it is simple, na? See, in this case, bottom plate is fixed and top plate is moving with constant velocity v. So this is the bottom plate, this is the bottom plate, this is the bottom plate, and this is the top plate which is moving with constant velocity, that is v, right? This is the bottom plate, and this is the top plate, this is the top plate, and the area of top plate which is in contact with the fluid, area of top plate which is in contact with the fluid, let us consider that is A. Now what is my question? My question is, what is the power required? What is the power required? Power required to power required for the plate, for the top plate, for the top plate to maintain constant velocity v, to maintain constant velocity v, right? So it is very simple. Simply you can say shear stress experienced by the top plate, shear stress experienced by the top plate multiplied by velocity of the top plate, and the velocity of the top plate, that is v, right? Now see, there is a fluid now, obviously in between these two plates there is a fluid. So this is the fluid, right? And since top plate is moving with constant velocity v and the bottom plate is stationary, and if you draw the velocity profile, so obviously we know each layer having different velocity, each layer having different velocity. So let us assume this velocity variation let us assume that velocity variation is linear. So velocity profile, let assume velocity profile, assume velocity profile is linear. Assume velocity profile is linear. So let us assume velocity profile is linear. So this is the velocity profile that you have. This is the linear velocity profile. Right? This is the linear velocity profile. This is the linear velocity profile. Right? So if I ask you what is the shear stress experienced by the layer, so since the velocity profile is linear, so we can say each layer experiences the same shear stress. So calculate shear stress. So shear stress experienced, we already discussed this part in detail in previous session. So shear stress experienced by layers. So we can say from the Newton's law of viscosity that tau at any y is equal to mu du by dy at that y. Right? And since velocity profile is linear, so simply we can write mu multiplied by delta u by delta y, or we can say mu multiplied by top plate velocity minus bottom plate velocity divided by gap. And let us consider this gap is h. So bottom plate is stationary and top plate is moving with velocity v. So we can write this is mu v by h. We can simply say mu v by h. So this is the shear stress. Now if you want to calculate the shear force, so it is very simple, right? We know that the shear stress is equal to shear force divided by area, right? So what is the shear force? This is a tau multiplied by a multiplied by, we can write v. And what is the tau? This is mu v, right? This is mu v by h into a, and here also v, so we can write mu v square by h into a. So this is the power required for top plate to maintain the velocity v. We already discussed this part in a detail, right, in previous class. So is it clear to everyone? And if you want to draw the shear stress variation, so we know that each layer experiences the same shear stress. Why it is so? Because velocity profile is linear. Okay, now come to the next case, right? Next case, right? Again, what I'm assuming here, bottom plate is fixed and the top plate is moving with constant velocity v, right, as shown. Now see, now come to the next case, which is a case number 2. So let us consider this is the bottom plate. Let us consider this is the bottom plate and this is the top plate. This is the top plate. Top plate is moving with constant velocity v, right? And in between top plate and the bottom plate, this is the bottom plate. This is the bottom plate. This is the top plate, right? And in between these two plates there is a liquid. So let us consider this is the liquid number 1. Let us consider this is the liquid number 1 and let us consider this is the liquid number 2. Right? There is 2 liquids. Right? This is the liquid number. This is the liquid number 1 and this is the liquid number 2. Right? Now liquid number 1 having dynamic viscosity, let us consider that is mu1, and the liquid number 2 having dynamic viscosity, let us consider that is mu2. Now if I'm talking about the height of liquid number 1, if I'm talking about the height of liquid number 1, so this is the height of liquid number 1, this is the height of liquid number 1, this is the height of liquid number 1, let us consider this is the H1, and this is the height of liquid number 2, so let us consider that is a H2. Now here also I am assuming that velocity profile is linear. Here also I am assuming that velocity profile is linear. Assuming linear velocity profile. Assuming linear velocity profile. Here also I am assuming linear velocity profile. Okay, so if you draw the velocity profile here, if you draw the velocity profile here, if you draw the velocity profile here. So first tell me guys, right, velocity profile is linear, so that velocity profile is a continuous line, or the slope will change. It is a continuous line. Is it continuous line? Tell me, if I am considering the linear velocity profile, is it continuous line or line should be discontinuous? Line should be continuous or line should be discontinuous? Yes, absolutely correct. Line should be discontinuous line. Why? Because right, this fluid having different viscosity and this fluid having different viscosity. Right, since both the fluid having different viscosity, that's why this line is not continuous line. This line is not continuous line. This line is a discontinuous line. So if you draw the actual velocity profile, so your velocity profile is, let us consider like this. Let us consider like this. This is the velocity profile. This is the velocity profile. Okay, this is the velocity profile. Is it clear to everyone, beta? Is it clear to everyone? Is it clear to everyone? Okay, so this is the velocity profile. Fine. Now let us consider interface velocity. If you see the interface, if you see the interface of these two liquids, if you see the interface of these two liquids, so let us consider this interface having velocity, let us consider VI. So what is the VI? That VI is, what is the VI? That VI is velocity at the interface. Velocity at the interface. Right? Let us consider that VI is the velocity at the interface, whereas V is the velocity of the top layer. Fine. Now what is my question? What is my question? My question is same. What is the force which is required to pull the top plate? What is my question? What is my question? What is the force? What is the force? What is the force required? What is the force required to pull the top plate? To pull the top plate with velocity V. Or in terms of the power, what is the power which is required? What is the power which is required to pull the top plate with constant velocity V? So simply we can say the force required, simply we can say now beta, that force required is equal to tau experienced by the top plate, tau experienced by the top plate multiplied by A. What is the A? The A is the area of the top plate which is in contact with the fluid number 1. So what is the area of the top plate? Area of the top plate is A. Area of the top plate is A. So can we write shear stress experienced by the top plate? Beta, can we write shear stress experienced by the top plate? Can we write shear stress experienced by the top plate? Can we write? What is the shear stress experienced by the top plate? What is the shear stress experienced by the top plate? So it is simple now. What is the shear stress experienced by the top plate? Top plate is in contact with the fluid number 1. So we can write this is the mu1 multiplied by mu1 multiplied by, right, mu1 multiplied by delta u by delta y in fluid number 1 multiplied by area, and this is equal to, we can write mu1 multiplied by, now what is the delta u? So we can write delta u is u top minus interface, right? So simply we can write this is the v minus vi divided by what is the delta y? That is the h1 multiplied by area, right? So this is the shear force, this is the resistance force which is experienced by this top plate. Is it clear to everyone? Is it clear to everyone? Right? Don't write na v minus, don't write v minus 0 divided by h1 plus h2. Right? Most of the students make mistake here. If I ask you what is the shear stress experienced by the top plate, they write, sir, it is mu1 multiplied by v minus 0 divided by h1 plus h2, right, like this. This is absolutely wrong. This is absolutely wrong, beta. This is absolutely wrong. Is it clear to everyone why it is wrong? Why it is wrong? Because fluid is not continuous, no? Fluid is not continuous, right? This fluid is a different fluid, this fluid is a different fluid. So we can't write like this. Is it clear or not? This expression is clear or not? Tell me. This expression is clear or not? Tell me. Right? So what is the force required? That force required is, we can write mu1 into v minus vi by h1 into a, right? So this is the force, shear force on top plate, that is equal to mu1 into v minus vi divided by h multiplied by a. Fine. Now can we calculate vi? Can we calculate vi? Can we calculate velocity at the interface? Can we calculate velocity at the interface? Can we calculate velocity at the interface? Beta, can we calculate velocity at the interface? Can we calculate? Vi. Vi is the interface velocity. Interface velocity. What is the Vi? That Vi is the interface velocity. Can we calculate the Vi? So if you draw the free body diagram of interface velocity, interface layer, if you draw the free body diagram of interface layer, this layer, right? So beta, this layer experience shear stress, this layer experiences shear stress by this fluid also, and interface layer experiences the shear stress by this fluid also, right? So that interface layer experiences the shear stress by this fluid also and by this fluid also. So if you draw the free body diagram, of interface layer, now above this interface layer, there is a layer of fluid number 1. There is layer of fluid number 1. And below the interface layer, there is a layer of fluid number 2. Is it clear or not? Is it clear or not? Right. So this is the layer. This is the layer of fluid number 1, and this is the layer of fluid number 2. And this is the interface layer. This is the interface layer. This is the interface layer. interface layer. Now, if you show the, right, if you show the shear stresses or shear forces, you can say, right, if you show the shear forces on this interface layer. Now beta see, if you see this layer and this layer, if you see this layer and this layer, please try to understand that this is a very, very conceptual part. Please try to understand this thing. This is very, very, very conceptual part. If you consider this layer and this layer, so obviously the layer number 1 having more velocity as compared to the interface layer. If you compare this layer and this layer, so obviously the layer number 1 having more velocity, as compared to interface velocity, right? Now, if I'm talking about the shear force direction, in the plate, in the layer number 1, so layer number 1 try to move in a positive x direction. So if you show the shear force or resistance force in the layer number 1, so in the layer number 1, this is in this direction, in opposite direction, right? And if I'm talking about the interface layer, so in the interface layer, it is in positive, in the positive x direction, right? So if I'm talking about the layer number 1, please try to understand this thing. If I'm talking about the layer number 1 and the interface layer, which layer having more velocity? Obviously the layer number 1 having more velocity. So first think about the resistance force direction in a layer having more velocity, right? How you decide the direction of friction force in two bodies? If I'm talking about the, let us consider two objects. Let us consider this is the object number A and this is the object number B. This object is moving with velocity of 10 meter per second, and this object is moving with a velocity of 5 meter per second. So how you decide the direction of friction force? So if you draw the free body diagram of a layer, or first we draw the free body diagram of an object having more velocity. So which one having more velocity? Block A having more velocity. So this block is moving with a velocity of 10 meter per second in a positive x direction. So what is the direction of friction force? This is the direction of friction force. Right? And if you draw the free body diagram of block number B, so in block number B, how this friction force act? Right? Just opposite to this, that means in this direction. Is it clear to everyone? Beta, is it clear to everyone? How you decide the direction of friction force? First, try to understand this part. How you decide the direction of friction force? To decide the direction of friction force, first consider a body having higher velocity or having more velocity. So first draw the direction of friction force on a body having higher velocity. Then draw the friction force direction in another body. Tell me this concept is clear or not? Or should I repeat this one? Tell me this concept is clear or not? Better tell me this concept is clear or not. If this concept is clear, then you can understand this part easily. So I want your reply in a chat box. This should be crystal clear, na? Then you can understand this part. So better see, if you see the interface layer and the layer number 1, so obviously the layer number 1 having more velocity, right? Layer number 1 having more velocity. So first show the direction of shear force in layer number 1. So in layer number 1, if I'm talking about the layer number one tries to move in a positive x direction. So what is the direction of resistance force? What is the direction of shear force? The direction of the shear force is negative x direction, right? And this layer number one is in contact with the interface layer. So if I'm talking about the interface layer, so in the interface layer, that resistance force or friction force in the positive x direction. Okay, now compare interface layer and the layer number two. Which one having more velocity, beta? Which one having more velocity? Which one having more velocity? If you compare layer number two and the interface layer, which one having more velocity? Which one having more velocity? Obviously, the interface layer having more velocity. Obviously, that interface layer having more velocity, and since interface layer having more velocity, you are comparing interface layer and the layer number two. Now, first show the direction of friction force or resistance force in the interface layer because of the fluid number two, right? So in the interface layer, friction force because of fluid layer 2, see, right? Interface layer is trying to move in a positive x direction, so that friction force because of layer number 2 is this fs2, right? Now I will show you interface layer only, beta. I will show you the interface layer only. This is the interface layer. This is the interface layer. This is the interface layer. Interface layer having velocity vi, right? And if you see the shear forces, so beta, this is the fs1 and this is the fs2. Is it clear to everyone? Is it clear to everyone? Very good, very good, very good. Right? Now we know that summation f, because this plate is moving with constant velocity v now. So velocity is constant. If velocity is constant, that means acceleration is 0. Right? Velocity is constant, that means acceleration is 0. So summation fx is equal to, we can write max. Since v is constant, therefore acceleration is 0. So simply we can write, beta, summation fx is equal to 0. And what is the summation fx? This is the fs1 minus fs2 is equal to 0. So simply we can write fs1 is equal to fs2, right? Or we can write that tau1 is equal to tau2. If you multiply both sides with area is same, right? So if you multiply with area both sides, so simply we can write tau1 is equal to tau2. Tau1 is equal to tau2. Is it fine? Now tau1 is equal to tau2. If this part is clear, so we can write tau1 is equal to tau2. Now beta, tell me what is the tau1. Now tell me, beta, what is the tau1? What is the tau1? Sir, tau1 is nothing but the sir v minus, sir, tau1 is nothing but the v minus vi divided by, or just 1 minute, this is the mu1 multiplied by delta u by delta y in fluid number 1, and this is equal to, what is the tau2? The tau2 is, this is the mu2 multiplied by delta u by delta y in fluid number 2. Right? Now mu1 multiplied by, now tell me what is the delta u by delta y in fluid number 1? So beta, this is v minus vi, divided by h1 is equal to mu2. Now what is delta u by delta y in fluid number 2? See, in fluid number 2, so it is vi minus 0 divided by h2. Vi minus 0 divided by h2. Right? Now we can easily calculate vi. So tell me what is the vi, right? So we can easily calculate vi. So beta, this is mu1 and this is v minus vi divided by H1 is equal to, this is mu2 into Vi divided by H2, right? Now this is V minus Vi by H1 multiplied by H2 divided by, this is Vi is equal to, right? This is mu2 by mu1, mu2 by mu1. Okay, now this is V by Vi minus 1 is equal to V by Vi, V by Vi by Vi, right? So V by Vi minus 1, and this is mu2 by mu1 into, mu2 by mu1 into, this is the H1 by H2, H1 by H2. So simply we can write, V minus Vi, or Vi is equal to, right? Vi is equal to, just 1 minute now. This is V by Vi, just 1 minute. V by Vi is equal to 1 plus, right? V by Vi 1 plus mu2 by mu1, mu2 by mu1 into H1 by H2, right? Mu2 by mu1, H1 by H2. And what is the Vi now? So that Vi is equal to, this is V upon 1 plus mu2 by mu1 into H1 by H2, right? So this is the interface layer velocity. Now your interface velocity in terms of all the known variables. Now see beta, now your interface velocity is in terms of all given variables. V is given, mu2 is given, mu1 is given, H1 is given, H2 is given. So your interface velocity, the interface layer velocity in terms of all given variables. Is it clear to everyone? Tell me, is it clear or not? Tell me, is it clear or not? Is it clear or not? Tell me, is it clear or not? So force required, what is our ultimate objective? Ultimate objective is force required for top plate, force required for top plate to maintain, or force required for the top plate, force required for the top plate, force required for top plate to pull it, force required for the top plate to pull it. Is it clear? Very good. Now this is equal to, you can write, now you can write mu1, H1, right? This is the mu1 into V minus Vi divided by H1 into A na. So this is beta mu1 by H1 into mu1 by H1 into A into V minus, what is the Vi? That Vi is V upon 1 plus mu2 by mu1 into H1 by H2, right? So simply we can write V into A into mu1 H1 into 1 minus 1 upon 1 plus mu2 by mu1 into, this is H1 by H2, right? This is the force required, for top plate to pull it. Is it clear or not? Tell me fast, is it clear or not? Now see, if you want to simplify this, so that force is equal to force required for the top plate. This is V into A, and this is mu1 by H1, right? And this is 1 plus mu2 by mu1, 1 plus mu2 by mu1, 1 plus mu2 by mu1 into H1 by into H1 by H2 minus 1 upon 1 plus mu2 by mu1 into H1 by H2, right? Now this is equal to plus 1 minus 1 is cancel out. Now mu1 H1, mu1 H1, so this is V into A into, right? Now if you multiply mu1 H1, so mu1 H1, so what you are getting, mu2 H2 upon 1 plus mu2 mu1 into H1 by H2, right? Like this. Or we do one thing, if you multiply with mu1 H1, if you multiply with mu1 H1, then this is equal to V into A, right? This is a mu1 H1, see, right? Mu1 H1, just 1 minute, na? I'm arranging the term in a very good manner. So I'm multiplying with mu1 by H1 here, and I'm multiplying by mu1 H1 in the denominator. So this is V into A into mu1 H1 into mu2 H2 upon mu1 H1 plus mu2 H2. Yes, this is a very nice expression you can see. F top. Now you can write F top. See, you can write F top is equal to V multiplied by A multiplied by V multiplied by A multiplied by mu1 H1 mu2 H2 upon mu1 H1 plus mu2 H2. Right, this is the F top. Right, so there is no need to remember this expression, na? But there is no need to remember this expression. There is no need to remember this expression. Just use your basic concept. Just use your basic concept. Right, on the basis of your basic concept, you can comment on this F top. Right, so there is no need to remember this expression. Now this is clear or not? Tell me, this is clear or not? This is clear or not? I'm arranging the terms, na? I'm simply arranging the terms, right? I'm taking v as a common, so it is 1 minus 1 upon 1 plus mu2 by mu1 into h1 by h2. Now I'm taking LCM, right? So if you take the LCM, then it is 1 plus mu2 by mu1 into h1 by h2. Now 1 plus mu2 by mu1 h1 by h2 minus 1 and 1 is cancel out. Now what I am doing here, I am multiplying with mu1 h1. I am multiplying with mu1 h1 in the numerator and the denominator. So then end of the day I am getting this one, right? So this is the final expression. This is the final expression. This expression is clear. Okay, and once you know the power, once you know the force required to pull the top plate, then you can easily calculate the power, right? Power required to pull the top plate, and that is simple: shear force or force experienced by the top plate multiplied by the top plate velocity, and that is V, right? So you can easily calculate the power required to pull the top plate. Okay, so I hope you can understand this. I hope you can understand this. Now come to the case number 3. Come to the case number 3. Force required to move the thin plate with constant velocity v as shown, and in this case top plate and bottom plate both are fixed. Right, in this case top plate and bottom plate both are fixed. So beta, let us consider this is the top plate and let us consider this is the bottom plate. Right, top plate is fixed, also bottom plate is also fixed, both the plate are fixed like this, right? And there is a thin plate, there is thin plate, so this plate is very thin, right? And in this side let us consider there is a fluid number 1. Let us consider fluid number 1. Fluid number 1. And in this side let us consider there is a fluid number 2. Both the fluids are different, so let us consider in this side there is a fluid number 2. Right, fluid number 1 having dynamic viscosity mu1, fluid number 2 having dynamic viscosity that is mu2, right? And this gap, let us consider this gap is h. Let us consider this gap is h. Now what is the question? What is the question? Question is, what is the force required to move this thin plate? So this is the thin plate, right? Can anyone tell me? Thin plate. What is the force required to move the thin plate with constant velocity v? So this plate is moving with constant velocity. So can anyone tell me force required to pull the thin plate with constant velocity v, with constant velocity v. So can anyone tell me what is the F? What is the F? What is the force F required to pull this plate, or to pull this thin plate with constant velocity v? Okay, so first draw the free body diagram, beta. First draw the free body diagram of this thin plate. First draw the free body diagram of this thin plate. So let us consider this thin plate, right? I'm applying force F. I'm applying this force F, and because of this force F, plate is moving with constant velocity v. Right, now I already told you, if in a problem velocity profile is not mentioned, then assume linear velocity profile. I already told you this, right? So in this problem also the velocity profile is not mentioned. So assume that velocity profile is linear. Assume linear velocity profile. Right, now if you draw the velocity profile, so this is the velocity profile now. See, right, this is the velocity profile now. Sorry, this is the velocity profile. I'm sorry. Right, this is the velocity profile. right? This is the velocity profile. This is the velocity profile. Is it clear? Now, draw the free body diagram, of this thin plate. Now, this plate is moving with a velocity v. This plate is moving with a velocity v. So, what is the direction of shear force on this plate? Or what is the direction of resistance force on this plate? Plate is moving in the positive x direction. So, direction of shear force or direction of resistance force on this plate, on this thin plate. So, this is the shear force applied by layer number 1, or you can say this is the shear force applied by liquid number 1, and this is the shear force applied by liquid number 2, right? And since plate is moving with constant velocity, so simply we can write the summation fx is equal to max. And what is this max? That is 0. Ax is 0, acceleration is 0. Why it is 0? Because plate is moving with constant velocity, so acceleration is 0. So we can write summation fx equal to 0, and summation fx equal to 0, so that f is equal to beta, f is equal to, simply we can write fs1 plus fs2, right? This is the shear force experienced by the thin plate, or this is the friction force on the thin plate. Is it fine? Is it fine or not? So F is equal to Fs1 plus Fs2. F is equal to Fs1 plus Fs2. Okay. Now what is the area of this thin plate? So let us consider area of this thin plate is A. A is the area which is in contact with the fluid. So F is equal to, or first calculate the Fs1. Fs1. So what is the Fs1? This is the tau 1 multiplied by area. Right, Fs1 tau 1 multiplied by area. And what is the tau 1 from the Newton's law of viscosity? From the Newton's law of viscosity we can write v minus 0, right? Okay, and one thing, the total gap between these two plates is h, na? Total gap between the top plate and the bottom plate is h, right? Now what I'm considering here, let us consider this plate is at a distance y, from the bottom plate. Let us consider the total gap is h. Please try to understand, na beta. Total gap is h. And let us consider this plate is at a distance y from the bottom plate. So if this is the y, what about this? This is the h minus y. This is the h minus y. Total gap is h. And this thin plate is at a distance y from the bottom plate. So what about the top plate? That is the h minus y. Right, now find the tau 1. So if you calculate the tau 1, so what is the tau 1? What is the tau 1? So simply we can write this is the mu 1 multiplied by velocity profile is linear, na? So that is v minus 0 divided by h minus y into a, right? What about the Fs2? This is equal to mu 2 multiplied by v minus 0 divided by y into a, right? So this is the Fs1 and this is the Fs2. Okay, so what is the force F? That F is Fs1 plus Fs2. So this is equal to mu 1 into v upon, right, Fs1, mu 1 into v upon h minus y into area A into area A plus mu2 into V by Y into A. Right, so this is the total force. Right, so we can take V and A as a common. So we can write mu1 upon H minus Y plus mu2 upon Y. Right, so this is the total force F which is required to pull the thin plate with constant velocity V. This is the force F which is required to pull the thin plate with constant velocity V. Is it fine? Is it clear? Is it clear or not? Is it clear or not? Okay. Now see, if you see this mathematical expression, beta, if you see this mathematical expression, then it is very much clear your F is function of Y. Right? See, V is a velocity of the thin plate which is constant. A is the plate area that is also constant. Mu1 is the viscosity of the fluid number 1. Mu2 is the viscosity of the fluid number 2. Right? These are constant. H is also constant. Right? H is the total gap between the top plate and the bottom plate. Now, if you see this mathematical expression, then it is very much clear now. Force required to pull the plate with constant velocity V is a function of Y. It is clear now. Tell me. That force F which is experienced by, or force F which is required to pull the thin plate is a function of Y now. Tell me. Is a function of Y. So if you place the plate here, if you place the plate here, your F is different. If you place the plate here, F is different. If you place the plate here, F is different. If you place the plate, F is different. So F is the function of Y. It is very much clear from this mathematical expression. It is very much clear. Force F is the function of Y. Okay, so tell me, can we make some exercise to calculate the F minimum? Right? Can we do some calculation to get F minimum? What is the minimum force? Required for the plate? Can we calculate F minimum? Because we know that F is a function of Y. Right? F is the function of Y. Now, what is my objective? My objective is calculation of the minimum force required to pull this thin plate. Right? Can we do some calculation for this F minimum? Can we do? Yes, we can do. We know the concept of maxima minima. We know the concept of maxima and minima. So to get F minimum, now differentiate F with respect to variable, and what is the variable? That variable is Y. So dF by dy is equal to 0. Right? So dF by dy, so F, that is V into A into mu1 upon H minus Y plus mu2 upon Y. Right? Now differentiate. So if you this is equal to 0 na beta, this is equal to 0. Okay, so V is 0, A is 0. Now differentiate this. So mu1 H minus 1 to the power minus 1 na? So this is mu1 H minus 1 to the power minus 1. So this is minus 1 Now h minus 1, differentiate h minus 1. So this is h minus 1 whole square into, now differentiate h minus 1. So this is minus 1, minus 1. So this is the differentiation of this term, right? This is the differentiation of this term. Not differentiate this, right? Plus mu 2 y to the power minus 1. So this is minus 1 upon y to the power minus 2, and y to the power minus 2, that means 1 upon y square, right? Now see here, so we can write this is a mu 1 upon, right, minus 1 plus 1, mu 1 upon h minus 1, h minus y whole square minus mu 2 by y square is equal to 0, right? Now h minus y by y, h minus y by y whole square is equal to, that is mu 1 by mu 2. Is it clear to everyone? Right? Mu 1 by h minus y square is equal to mu 2 by y square. Right? Now mu 1 by mu 2 is equal to h minus y square upon y square. So we can write in this way, h minus y upon y whole square is equal to mu 1 by mu 2. Or simply we can write h minus y by y is equal to plus minus root over mu 1 by mu 2. Right? Till this point it is clear to everyone? Tell me guys, till this point it is clear to everyone? Till this point it is clear to everyone? Tell me. Till this point it is clear to everyone? Okay, so if it is clear to everyone, then see that h minus y by y is equal to plus minus root over, right? H minus y by y is equal to plus minus root over mu 1 by mu 2, right? And we can write this is a h by y is equal to 1 plus minus root over mu 1 by mu 2, right? And we know that h is greater than y, right? We know that h is greater than y, h is greater than y, na? H is greater than y. So this value must be greater than 1, na? H is greater than y, h is greater than y, we know that. Since h is greater than y, then this value must be greater than y, greater than 1, I'm sorry, h is greater than y, so this value must be greater than 1. That's why minus sign is not possible. If you see this expression, minus sign is not possible. So since h is greater than y, therefore minus sign is not possible. Therefore minus sign is not possible. And since minus sign is not possible, so we can write h by y is equal to, this is 1 plus root over mu 1 by mu 2, or we can say y is equal to this is h upon 1 plus root over mu 1 by mu 2, right? This is the y, right? So this is the y, this is the minimum y, I'm sorry, this is the y corresponding to that, this is the y corresponding to that f is minimum. This is the y corresponding to that, this is the y corresponding to that f is minimum, right? And if someone asks you what is the f minimum, so it is very simple, right? You have mathematical expression of f, just put this value, right? Just put this value of y, this value of y in this expression. So you will get the F minimum. Right? Let us consider this y as equal to y dash. Let us consider beta, this y is equal to y dash. So what is the F minimum? What is the F minimum? So that F minimum is equal to, we already have mathematical expression of F. So F minimum, this is V multiplied by A, right? Mu1 H minus y dash plus mu2 y dash. Right? So you can calculate F minimum from here. And what is the y dash? This is the y dash H upon 1 plus root over mu1 by mu2. F is minimum, na? F is minimum. Why it is maximum? F is minimum, beta. Okay, do one thing. If you want to, if you have any confusion related to this, sir, F is minimum or maximum, because this is a condition corresponding to the maximum and minimum. So do one thing, double differentiate, na? Right? Double differentiate this expression. Double differentiate this expression. Right? And if you perform double differentiation, then definitely you will get the positive value. Definitely you will get the positive value corresponding to this y dash. Definitely. So if you have any doubts, sir, this F is minimum or maximum, because this is the condition corresponding to maximum. This is the condition corresponding to maxima or minima. So if you have any doubt, perform double differentiation, right? Perform double differentiation, right? And once you perform the double differentiation, then put this value of y dash, then definitely you will get that double differentiation value is greater than 0. Double differentiation value is greater than 0, and we know that double differentiation value is greater than 0. That means at this particular y, your F is minimum. Sahib, is it clear? So this is your case number. This is your case number 3. This is your case number 3. So again I am repeating, guys, there is no need to remember any mathematical expression or any end expression that we are getting, right? There is no need to remember this one. No? There is no need to remember this one. There is no need to remember this one. You just remember the Newton's law of viscosity. That's it. And once, right, you know that Newton's law of viscosity, and in a different cases, how I am applying that Newton's law of viscosity. My basic concept is Newton's law of viscosity, right? Then in a different cases, I am just applying the Newton's law of viscosity, right? Okay. Now, come to the next case. Now come to the next case. Next case, top plate, bottom plate fix. Top plate, bottom plate fix as shown. See, top plate, bottom plate fix as shown. As shown. Right, top plate and bottom plate both are fixed as shown. Now see, this is top plate. This is top plate, and this is the bottom plate, right? And in between top plate and the bottom plate, in between top plate and the bottom plate, there is a fluid, right? There is a fluid. Okay, now I want to find out the shear stress experienced by the top plate and the bottom plate, right? So this fluid is flowing in between two fixed plates, right? This fluid is flowing in between two fixed plate. This is the top plate, this is the bottom plate, and both the plates are fixed, right? Now see here, what is my objective here? What is my objective? What is my objective? My objective is calculation of shear stress experienced by the top plate and the bottom plate. What is my objective? My objective is calculation of, or what is my objective? To find the shear stress experienced by the top plate and the bottom plate. Shear stress experienced by top plate or bottom plate. Top plate or bottom plate. Now better tell me one thing, in this problem there is a symmetry. Tell me one thing, in this problem there is any symmetry? Are you able to see the 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 symmetry in this problem? Tell me fast. Are you able to see the symmetry in this problem? Yes. Yes, na? There is symmetry, na? Right, there is a symmetry. There is symmetry about this axis. There is symmetry, na? Right, and I want to use that symmetry, right? I want to use that symmetry. And that's why for this problem why the distance is taking from the center line. Why I am taking, right? This is my reference axis, beta. This is the x axis and this is the y axis. Please try to understand this, right? To use the symmetry or to take the advantage of symmetry, what I'm doing here, right? I'm considering y is equal to 0 at the center line. Y is equal to 0 at the center line to take the advantage of symmetry. Is it fine? Okay. Now if you understand this, so at the center line y is equal to 0 and this is your y direction. This is your positive y direction and this is your negative y direction. If this is your reference axis, if this is your reference line, then above the reference line positive y and the below the reference, that is negative y. Right, most of the student may have some question here, sir, why you are not taking y from here in most of the problem? So far whatever the problem we discussed, you take y from the bottom plate, you take y from this plate. So sir, why you are not taking the y from here? We can take, no problem, but I want to take advantage of the symmetry. I want to take advantage of symmetry that is present in this problem. Okay, that's why I'm taking center line as a reference. So y is equal to 0 at the center line. Above the y, that is a positive. Below the y, that let us consider that is negative. And better, let us consider gap between these two plates as 2h. You can take h also, no problem. But to make the problem simplify, what I am doing here, gap between top plate and the bottom plate, I am considering as a 2h. Right, now what is my objective? Obviously my objective is calculation of, what is my objective? Calculation of shear stress experienced by the top plate and the bottom plate. This is my objective. What advantage we can take from the symmetry? Yes, definitely, right? Once explanation is completed, then definitely you can understand this better. Okay, just wait and watch. Okay, now see, In this case, what I'm assuming, I'm not assuming velocity profile as a linear, right? Let us consider in between these two plates, the velocity profile is non-linear, and that follows the velocity profile is non-linear. If velocity profile is linear, then it is very, very simple. Now I am considering velocity profile as non-linear. Velocity profile is non-linear. Velocity profile is non-linear, and that follows second degree parabola y is equal to a plus by plus cy square. Right? Y is equal to a plus by plus cy square. Right? This is the velocity profile. In this problem, what I am assuming here, the velocity profile is non-linear. And in a non-linear, it follows the second degree parabola. Y is equal to a plus by plus cy square. If velocity profile is linear, then problem is too much easy. But to problem make little bit difficult, what I am assuming here, I am assuming that velocity profile is non-linear, and in a non-linear, it follows a second degree parabola, that y is equal to a plus by plus cy square, right? Where a, b, c are constant. Where a, b, c are constant. Where a, b, c are constant. Where a, b, c are constant, right? Now, can we calculate a, b, c? Can we calculate ABC? For the calculation of ABC, boundary conditions are required. Na? For the calculation of ABC, boundary conditions are required. Remember, when we consider the linear velocity profile, right? U is equal to a plus by. So for the calculation of AB, boundary conditions are required, right? So we use boundary condition over there. In a similar fashion, in this particular velocity profile, there are three constants A, B, C. So can we find out these three constants A, B, C? Can we find out these three constants A, B, C? Can we find out? Yes. By this we need a boundary condition. For this we need a boundary condition. So can anyone tell me what are the boundary conditions? Can anyone tell me? Okay, how many boundary conditions are required? How many boundary conditions are required? Right. In this problem, A, B, C are constant. So if I ask you, how many boundary conditions are required? Obviously, 3 boundary conditions are required. Na? 3 constant, so we need 3 boundary condition. 3 constant, so we need 3 boundary condition. Right? What is the first boundary condition? Tell me, what is the first boundary condition? Tell me. So can we write at y is equal to plus h? At y is equal to plus h, u is 0 na? At y is equal to plus h, u is 0 na? At y is equal to plus h, u is 0 na? Yes. At y is equal to minus h, at y is equal to plus h, this is a fixed plate. So at y is equal to plus h, u is 0. At y is equal to minus h, u is equal to 0. Yes. And beta, can we write at y is equal to 0, that u become u maximum? At y is equal to 0, that u becomes u maximum, or beta we can say at y is equal to 0, that du by dy is equal to 0. That is the benefit of symmetry. We know that at y is equal to 0, that du by dy is 0. At y is equal to 0, that du by dy is equal to 0. This is the benefit of using the symmetry. Right? See, At y is equal to plus h, at y is equal to plus h, u is 0, fine. Right? At y is equal to plus h, u is 0, that's fine. At y is equal to minus h, u is 0, that's fine. Right? Three boundary conditions are required. So two boundary condition, these are the no slip, these are from no slip condition. Right? Now what is the third boundary condition? What is the third boundary condition? So if you have idea about the symmetry, if you want to take advantage of symmetry, right? That is your question, Ajit, right? Ajit, this is your question. What is the advantage of, what is the advantage that we can get from the symmetry? But this is the advantage. We know that at y is equal to 0, because this is the problem which is symmetry about this axis. So at y is equal to 0, the du by dy is 0. We know that. Is it clear? Is it clear or not? Is it clear or not? So your velocity profile is like this. If I draw the velocity profile, if I draw the velocity profile, your velocity profile is like this. Here the velocity is 0, here the velocity is 0, and here the velocity is maximum because du by dy is 0. Here velocity is 0, here velocity is 0, here velocity is maximum because du by dy is 0. So this is your velocity profile. This is the parabolic velocity profile. This is the parabolic velocity profile. I'm sorry. See? Right? In this portion, this is the velocity profile. In this portion, this is the velocity profile. Similar velocity profile you are getting in this portion also. So this is the benefit of symmetry. This is the benefit of symmetry. Okay, so this is your Now it is fine. Now it is fine. Now it is fine now. Now it is fine. Okay, so just simple, just simple. See, we have these three boundary condition. We have these three boundary condition. From third boundary condition, at y is equal to 0, u is equal to u maximum. Y is equal to 0, u is equal to u maximum, because du by dy is 0. So y is equal to 0, y is equal to 0, y is equal to 0, u is equal to u maximum. So a is equal to u maximum. Now use first boundary condition. So if you use first boundary condition at y is equal to plus h, u is equal to 0, u 0, a plus a value is u maximum. So u maximum plus bh plus ch square. U maximum plus bh plus ch square. If you see the second boundary condition, y is equal to minus h, u is equal to 0, u is equal to 0, 0 is equal to a minus bh plus ch square. Right? Now you have two equation and two unknowns, and those unknowns are b and c. So can you calculate b and c? Can you calculate beta b and c? Can you calculate b and c? Can you calculate b and c? So if you calculate b and c, easily you can calculate na, two equation and two unknown. Two equation and two unknown. So what you are getting, right? What you are getting? You are getting you are getting b is equal to 0. I'm just, right? See, bh plus ch square, bh plus ch square is equal to minus u max, na? Right? bh plus ch square is equal to minus u max, and minus bh plus ch square is equal to minus u max. Right? Now add these two equation. If you add these two equation, this is 2ch square is equal to minus 2 u max, minus 2 u max. 2 and 2 is cancelled out, so c is equal to minus u max by h square. Right? C is equal to minus u max by h square. Now calculate b. So if you calculate b, now put this value of c in expression number 1. So bh, right? bh minus u maximum h square into h square is equal to minus u maximum. Right? So h square is cancelled out. So ultimately what you are getting, that value of b as 0. Right? This is the value of c. This is the value of c. This is the value of b. So ultimately what you are getting, that u is equal to, a value is a maximum, b value is 0, ch square. Right? So this is minus c value is u maximum by h square into y square, So this is the velocity variation, 1 minus y square by h square. Fine, beta. This is the exact velocity variation. This is the exact velocity variation. Why this velocity variation is required? Why this velocity variation is required? Without velocity variation, it is not possible to comment on du by dy. Na? It is not possible. It is not possible to comment on du by dy. If it is not possible to comment on du by dy, then how you can calculate the shear stress? Right? It is difficult to calculate the shear stress. Okay, so this is the exact velocity profile. And if you apply the Newton's law of viscosity, right? So velocity variation is parabolic. Velocity variation is second degree parabola. Now if you apply the Newton's law of viscosity, that Newton's law of viscosity, if you apply the Newton's law of viscosity, the shear stress experienced by the any layer is equal to, that is mu du by dy at that y, and that is equal to right, mu into, not du by dy. So du by dy is, this is the u maximum, and this is minus 2y by h, right? So shear stress at any y is equal to, this is minus 2 mu u maximum into minus 2 mu u maximum minus 2 mu u maximum y by h, right? This is the shear stress mathematical expression at any y. This is the shear stress mathematical expression at any y. This is the shear stress mathematical expression at any y. Now tell me guys, velocity variation is second degree parabola. 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 What about the shear stress variation? What about the shear stress variation? Tell me, what about the shear stress variation? How the shear stress varies? How the shear stress varies? How the shear stress varies? So the shear stress variation is linear, right? The shear stress variation is linear. This is a shear. From here you can easily see y to the power 1 na? Y to the power 1, that means linear variation. So shear stress variation is linear variation. Shear stress variation is linear variation. And if you draw the shear stress variation, so tell me beta, at y is equal to 0, what is the shear stress? At y is equal to 0. At y is equal to 0, what is the shear stress? That is 0. And at y is equal to plus h minus s, the shear stress is maximum. Okay, so forget about the sign here. Na? Forget about the sign here, right? Focus on magnitude only, because in case of shear stress we need magnitude only, right? In case of shear stress we know we need magnitude only. We know the direction. Of shear stress. If I ask you what is the direction of shear stress on the top plate, so obviously opposite to the flow. If I ask you what is the direction of shear stress on the bottom plate, obviously opposite to the direction of the flow. We know that. So focus on magnitude only. So if you focus on magnitude only, so at y is equal to 0, shear stress is 0. At y is equal to 0, shear stress is 0. At y is equal to plus h or minus h, shear stress is maximum. And that shear stress variation is linear. So this is the shear stress variation. This is the shear stress variation. This is the tau w. This is the tau w. Right? This is the shear stress variation. The shear stress variation is linear. So if your velocity profile is non-linear or in a non-linear second degree, if your velocity profile is second degree parabolic, so shear stress variation is linear variation. So this is the velocity variation. This is the velocity variation. And this is the tau shear stress variation. Right? And what is the wall shear stress? So obviously that wall shear stress we can easily calculate. Wall shear stress or maximum shear stress, no? Wall shear stress or maximum shear stress. Wall shear stress or maximum shear stress. Right? Tau w you can say, or tau maximum you can say. Right? That is equal to that is y is equal to h, na? Y is equal to h. So that become 2 mu u max. Y is equal to plus minus h, na? Y is equal to plus minus h. So this become 2 mu u max. This is the 2 mu u max. This is the maximum or wall shear stress. Just 1 minute, na? Just 1 minute. Okay, just 1 minute. I'm sorry beta. I'm sorry. This is h square, na beta, h square. I'm sorry. Right? du by dy, na. So u maximum 1 minus 2y by h square. So beta, this is the h square, na. H square. H square. So y is equal to h. So this is 2 mu u maximum by h. Right? 2 mu u maximum by 2 mu u maximum by h. So this is the wall shear stress. This is the wall shear stress, or you can say maximum shear stress. Right? 2 mu u maximum by h. Is it clear to everyone? Tell me. So what is our objective? What is your objective? Objective is calculation of shear stress. Calculation of shear stress. What is the objective? Calculation of shear stress experienced by the top plate and the bottom plate. So this is the shear stress. This is the shear stress experienced by the top plate and the bottom plate. Is it fine? Is it clear? Okay, now tell me answer of some conceptual question. Tell me answer of some conceptual question. Question number 1. Tell me answer of some conceptual question. Okay, so question number 1. Question number 1. Let us consider a plate, and this plate is fixed. Above the plate, fluid is flowing, and fluid attains a linear velocity profile. Fluid attains a linear velocity profile. In this problem, fluid attains a linear velocity profile. Right? Now, consider another case. Again, I am considering bottom plate. Bottom plate is fixed and fluid is flowing over the bottom plate, and fluid layer attains parabolic velocity profile here. Fluid layer attains parabolic velocity profile here. Fluid layer attains parabolic velocity profile here. Okay, now let us consider this is the layer number 1 and this is the layer number 2. Right? This is the layer number 1, this is the layer number 2. So what is my question? My question is, what is the ratio of tau 1 by tau 2? Right? What is my question? My question is, what is tau 1 by tau 2? Tau 1 by tau 2. Tau 1 is the shear stress experienced by this layer. And what is the tau 2? Tau 2 is the shear stress experienced by this layer. Right? So my question is, what is the tau 1 by tau 2? In this case, for this question, right, tau 1 by tau 2 greater than 1, B. Tau 1 by tau 2 lesser than 1, option C. Tau 1 by tau 2 is equal to 1, and option D, cannot predict or cannot comment. Cannot comment. Okay, so this is the one question, question number 1. Let us consider this is the question number 2. So again, in question number 2 also, let us consider this is the layer number 1, this is the layer number 2. So that is the same question. What is the tau 1 by tau 2? What is the tau 1 by tau 2? Option A, tau 1 by tau 2 greater than 1. Option B, tau 1 by tau 2 lesser than 1. Option C, tau 1 by tau 2 is equal to 1, and option D, cannot comment, because data is not sufficient, right? Cannot comment because data is not sufficient. So this is the velocity variation, na beta, right? This is the velocity variation, u of y, u of y. In this case, velocity variation is linear, and in this case, the velocity variation is non-linear. What is your answer? Okay, so tell me answer for question number 1. So tell me answer for question number 1. In question number 1, velocity profile is linear, whereas in question number 2, velocity profile is non-linear. So what is the question? Question is tau 1 by tau 2 ratio. Tau 1 by tau 2 ratio. So tell me. हाइड्रोलिक भी आप पढ़ाएंगे सर ऐसे ही? हाइड्रोलिक अभी तो नहीं होगा, है ना दीपक? हाइड्रोलिक अभी तो नहीं होगा, अभी तो फिलहाल यही चलने वाला है, बट हाँ कभी फ्यूचर में अगर हुआ तो डेफिनेटली I will teach hydraulic also in same detailed manner. Okay, question number 1, that is B. Why it is B, beta? If I already told you, a number of times, if velocity profile is linear, then what about the shear stress variation? If velocity profile is linear, then what about the shear stress distribution? Beta, what about the shear stress distribution? If velocity profile is linear, then what about the shear stress distribution? Shear stress is independent of y na beta. Shear stress is independent of y na. Shear stress is independent of y na. If velocity profile is linear, then shear stress variation is independent of y na. This is the tau variation. So the shear stress experienced by the layer number 1 is equal to shear stress experienced by the layer number 2. That is same. That is same, beta. Shear stress experienced by the layer number 1 is equal to shear stress experienced by the layer number 2. That is same. So what is the tau 1 by tau 2? Tau 1 by tau 2 is equal to 1. Tau 1 by tau 2 is equal to 1. Why it is Bombay? Why it is Bombay? Chennai. Chennai is correct. Right? Chennai is correct. If velocity profile is linear, then each layer experiences the same shear stress. If velocity profile is linear, each layer experiences the same shear stress. So if I ask you what is the ratio of shear stress of these two layers, so the ratio of shear stress of these two layers is equal to 1. Okay, now come to this part. If see here, if velocity profile is non-linear, then what happened, or what is the ratio of tau 1 by tau 2? What is the ratio of tau 1 by tau 2? So first tell me, if your velocity profile is non-linear, let us consider second degree parabola. Let us consider beta second degree parabola. Let us consider second degree parabola. Let us consider this is a second degree parabola. Second degree parabola. It follows a plus by plus cy square. So your velocity profile is non-linear, follows a plus by plus cy square, non-linear velocity profile. So in this case, what is the shear stress variation? What is the shear stress variation? What is the shear stress variation? Can anyone tell me? What is the shear stress variation? Can anyone tell me what is the shear stress variation? So beta, if your velocity profile is second degree parabola, then the shear stress variation is linear. Shear stress variation is linear. And shear stress variation linear, we also know that that layer which is present at the surface, or layer which is near to the surface, experiences the maximum shear stress. See here, focus on this part only, 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 focus on this part only. Right, layer which are present at layer which are present near to the surface experiences the more shear stress. So if I draw the shear stress variation here, if I draw the shear stress variation here, if I draw the shear stress variation here, so this layer experience little shear stress, and as we are moving towards the plate, shear stress value increases, and how it increases? It increases linearly. It increases linearly. So this is the shear stress variation. This is the shear stress variation. This is the shear stress variation. Here shear stress is tau W. Right. Now, what is my question? My question is tau, what is the ratio of tau 1 by tau 2? So obviously, in this case, beta tau 1 is greater than tau 2. Obviously, in this case, tau 1 is greater than tau 2. And if tau 1 is greater than tau 2, then this ratio tau 1 to tau 2, this ratio is greater than 1. This ratio is greater than 1. So what is the correct answer? Correct answer is Agra. A is the correct one. Okay, is it clear? Is it clear or not? Is it clear or not? So I hope whatever we discuss in today's class, I hope whatever we discuss in today's class, that is clear, and not only clear, it should be crystal clear. I hope whatever the concept we learned today, that is clear to everyone. Fine. So remaining part of Newton's law of application, right? Remaining part of Newton's law, application of Newton's law of viscosity, remaining part of application of Newton's law of viscosity, that we will discuss in tomorrow's class. Okay, so thank you so much guys. Bye bye, take care, and have a good night everyone. Good night.